This lecture continues the work on normal distributions. So this lecture is about finding values for normal distributions given any desired probability that you are looking at. All right, so to find the values that correspond to a given probability, you first find the corresponding z-score and then use a standard normal table to find the desired values x. Okay. Here, if you have a normal distributions, and then you're looking at like certain probability, let's say 15% probability to the left of this value here, then you want to find, so if you look at the 50% to the left of this value, what is this value? So what is x1? So then before you can find x1, you need to find z1, right? The z is just the bridge that connects you from distributions to standard normal distributions. So using the z table, the standard normal table, and the probabilities here, you can find the z-score, z1, using the table. And once you have z1, you can find x1 using the formula that helps you find z1, right? Which is x1 minus mu divided by sigma. So in this case, I know z1, I know mu, I know sigma. I can find x1 equals to z1 times sigma, and I add to the mean of the distributions. Again, x is the value that I'm looking for. Probabilities is given, and the standard normal table can be used in this case. So first, let's practice on finding a z-score given an area. Okay. So find the z-score that corresponds to an area of 0.3662. Let's go to the z table. 0.3662 is less than 0.5. That means the z-score should be negative. And then again, using this table here, you know that the area, so you know that the numbers right inside this box are the areas, and the numbers on the first column and the first row are the z-score corresponding to this area. So now the area that we're looking at is 0.3664, 0.36, 0.366, 366. So okay, 366 is around here, right? And you say, let's look at this again. 3662. So 0.3662, and I found, oh, this 0.36693, which is a very close value to the 0.3662. And I found another one could be 0.37070, right? So between these two values are the values that very, very close to 0.3662. Between these two values, which one is closer? So which one has the shorter distance to the value that we're looking at? In order to do that, we just need to calculate the difference between the two, right? And take the absolute value because we're finding the distance. So we'll take 0.36693 minus 0.3662. You get 0.00007. So the distance here is 0.00073 is the distance. Okay, how about the distance between 0.37070 minus 0.3662 is 0.0045. Okay, apparently this value is closer to this value compared to this value. That is why the z-score that correspond to 0.3662 should be negative 0.34. Okay, not negative 0.033. So negative 0.034, it should be the answer here. Next one, the z-score that correspond to 0.8925. Okay. Again, the next one is 0.8925. We're looking at this value, and it's greater than 0.5, so we know that we need to go to the positive table. So 0.8925. Let's look at here, 8925, which is this one, right? 89251. Certainly is the closest value that I can find in this table, and this value corresponds to 1.24. So the z-score is 1.24. All right, how about 0.05? It's gonna be in the negative sign. Zero 0.05 is very small value. Let's look at 0.05. I found 0.05050. I also found 0.04947. Which one is closer? So I found the two values, right? You have 0.0505 and you have 0.04947. So the differences between these two values to the 0.05 is very close. I would say this is 0.00009, right? 1, 2, 3, 5. And this is like 0.00053. So these two values here are very, very close. Like the distance are super close to each other. So that's why we need to take the average of these two z values. So the z values for the 0.0050 here is negative 1.64. And the z values for 0.04947 is 1.65. And then we need to take the average of these two values. So you take the average of these two values, you will get negative 0.0645, which is the average. Okay. And negative 0.0645 will be the z value that corresponds to 0.05. Again, the reason why we're taking the average is because the differences or the distance between these 2 points to 0.05 are almost identical, the same, almost the same. So that's why we're taking the average. Versus the first values here, right? The first value, the distance from these 2 points are far away from each other. So this is 0.045 and this point 0.00073. So for sure that this one wins a fair game. But compare these two values, they are very, very similar. So that's why we're taking the average of the two. So the answer is negative 1.645. Okay. How about the z-score that correspond to 0.95? And then if you look at 0.95 and 0.05, they are the complements of each other because 0.95 plus 0.05 is 1. The complement of each other, that means the area, right? So 5% here. So the 0.05 is the 5% on the left, right? And 0.95 here is actually is this point here where you have 5% to the right, on the right. If you look at this z value, so that means the z values in that correspond to 0.95 is the opposite of the z value that corresponds to 0.05. So the z value, without using the table again, I know is positive 1.645. Again, if you look at this, 95 here should be the area to the right. If it's 95 to the right, then it should be 5% to the left. Sorry, if it's 95 to the left, then is 5% to the right, right? 0. So we know that because they are complement of each other, so we know that the z values are just the opposite of each other. All right, now we know how to find the z-score, then we can use that skill in order to find the corresponding x values for any given probability. So let's say water footprint, example number 7, a water footprint is a measure of the appropriate of fresh water. The per capita water footprint in megagallons in the US for a recent year can be approximated by normal distributions. If we now have normal distribution, I can draw a bell-shaped curve with a mean of 3.37. So the mean is 3.37. And the standard deviations of 0.18. Okay. The first question is, what water footprint represents the 80th percentile? So remember, 80 percentiles is a value which 80% of the population is less than that value, right? So that means I know the percentage and 80. So that means I know that the probability to the left of this value is 0.8 or 80%. I need to find the water footprint, which is the x value. What is x1? So I know the percentage, I can find the z values, right? That corresponds to the 80%. You see, 80% should be on the right side. I'm looking at 0.8. 0.8, I found this value, which is close, and I also found this value. Which one is closer? So 0.8, right? I found 0.79955, and this is a 0.234. 0.045, right? It's the distance, and 0.00234. So this values here has a closer distance compared to 0.8 by 10th, by 1 decimal place. So that means I'm going to take the z-score for this, taking this z-score here, which is 0.84 is a z-score. So I found the z-score is 0.84, okay, of the 80 percentile or 80%. Once I found the z-score, then I can find x1, right? I said z1, x1 equals to, according to the formula, it equals to z1 times standard deviation plus the mean, which is mu, right? And this is going to be 0.84 times 0.18 plus 3.36, and is equals to 3.5112, which is the water footprints that correspond to 80 percentile. What about the water footprint represents the 29 percentiles? So again, we have normal distributions. Now we look at the 29 percentiles, which is on the left, right? This is 29 percentile, okay? And again, we know mean, we know standard deviations. We just need to find the z that corresponds to 29 percentile. 29, so it should be on the left, 0.29. 0.29, I found this one, 116 and 29460. So for sure, 0.29116 is closer, or 0.28774. I think 0.55 should be 0.29116 is the answer. Yeah, this is a closer one. So the z-score should be -55. So then x2 equals to z2 times sigma plus mu equals to -0.55 times 0.18 plus 3.36. Which give you 3.261. Okay, so the x2 here is 3.261. It's the x value that corresponds to the 29 percentile. Okay, and then the next question is, what water footprint represent the third quartile? Do you remember the third quartile? So the third quartiles, that is the values, the quartile that correspond to the 75%, right? And 75% of the populations, the first 75% of the population is the third quartile. So if you look at here, the area here would be 75%. And you want to find the x3. And you still have the same mu and the same standard deviations. What is z3? That corresponds to 75%. So it should be the positive one. 75 So I look at 0.75175 and 0.4857. That looks very close. 57175 minus. They're very close actually, but the closer one is 0.74857. So the corresponding is 0.67. And then you can find x3 equals to z3 times sigma plus mu equals to 0.67 times 0.18 plus 3.36, which will give you 3.4806. So 3.4806 is the wider footprints represents the third quartile, and the third quartile corresponding to the first 75% of your populations. All right, look at the next example. Red blood cell count. The red blood cell counts in millions of cells per microliter for populations of adult males can be approximated by a normal distributions with a mean of 5.4 million cells per microliter and the standard deviations of 0.4 million cells per microliter. Again, if we have a normal distributions, then we should always draw a normal curve with the mean in the middle and the standard deviations maybe on the outside of it. And the question is, what is the minimum red blood cell count that can be in the top 25% of count? So top 25%, that means you're looking at the percentage on the right tail, right? So this is top 25%. And the right tail, you want to find the minimum values that can be in the top of 25% of count. You're looking at X1 here. Again, you have X1, then you need to find Z1 that corresponds to the top 25%. In order to find this Z1, we want to look at the Z that corresponds to the third quartile, right? 75%. And you know, 75% and 25% is actually a complement of each other. That means the Z-score here is just the same as the Z-score that I found up here. And then I can just find the X value, right? Which is the red plus cell count, which is the X value. Z1 sigma plus mu equals to 0.67 times 0.4 plus 5.4. 67 times 0.4 plus 5.4, which is 5.668. All right, and the units should be million cell per microliter. The units that you should include it. How about the next one? What is the maximum red blood cell count that can be in the bottom 15%? So I have this here. Bottom 15%, that means it's a 15% on the left of the distributions, right? So in order to find the maximum, in the bottom, you have a maximum value. You need to find Z. that corresponds to 15%. Z2 equals to what? 15%, which is on the left side, 0.15. 0.15. So I found this value and this value. Which one is the closer one? So the closer one is this value, actually, because the difference is 0.00083 compared to the other one. So the z value is negative 1.04. All right, then I can find the x value, which is z2 times sigma plus mu is negative 1.04 times 0.4 plus 5.4, which is 4.984, again, million cells per microliter. All right. And look back in my previous unit, a previous example. Look what I forgot. I forgot to add the unit for this. So for this answers, right? The units is mega gallons. We just want to have like a habit on adding units for any of the answer that that should have a unit added to it. So mega gallons and when you find the values, but your value should come with a unit, right? If you find probability, then it's just probability. Percentage, then you have percentage as a unit. Okay, so this lecture again helps you find the values for normal distributions. Again, when you have a normal distribution of variable, continuous random variable that is normally distributed, and then you're given a probability, then you can use a z-table to find a z-score that corresponds to that probability. And then you use the formula here to find the x value that corresponds to that probability.